Hello and welcome to week 2, lecture 3 of CO 442642 graph theory. Today we'll be going beyond Brooks Theorem. So to remind you again what Brooks Theorem was, the theorem by Brooks from 1941 says that if G is connected, then chi of G is in most delta of G if and only if G is neither complete nor an odd cycle. Again, recall that is asking how to save one color from the greedy bound of delta plus 1, and the answer was to forbid the obstructions of being complete or an odd cycle, where we had to assume connected as you could just add other vertices and other components without really affecting the chromatic number. Alright, but the question next then is, can we go further? This is a theorem from 1941, that's almost 80 years ago. Where else can we go? What generalizations or strengthenings or variants can we do? So what I'd like to talk about today is, can we save more colors? Can we do more than just plus 1? Can we go to delta minus 1 for the number of colors? Delta minus 2, half delta, even lower. So all these will be questions we'll be getting at, and under what conditions. So here, it may be not clear, it's really just answering for Brooks exactly when you can save that 1, but maybe instead let me think of it in this form. This omega delta chi paradigm. Namely, I want to suggest the odd cycles are a bit of the odd man out in that theorem, and what's really important are the cliques. So what is the maximum chromatic number of graphs with omega g at most omega and delta of g at most delta? So this is a very nice question, right? If we kind of forbid large cliques and fix the maximum degree, what is the correct number for the chromatic number as a general bound? And in this terms, then we could reformulate Brooks maybe as, let's exclude the delta equal 2 case. So if G is a graph with delta at least 3 and omega is at most delta, so we exclude k delta plus 1, then Brooks says that chi is at most delta. So this is fragmenting Brooks into a delta equal 2, where it's just the normal kind of odd cycle bipartite type case, and a delta at least 3 case where we're just forbidding the cliques. And that's maybe a better way to think about Brooks, and that's how we approached at least the formal proof to make it easier for ourselves. So then Brooks theorem answers the question when you want to only add the condition that omega is the most delta. What about going on? Can we save another color? So saving one extra color, there is actually a very nice conjecture about this by Borodin and Kostachka from 1977. And it says the following: if G is a graph with delta of G at least 9 and omega of G at most delta of G minus 1, then you can actually get chi of G at most delta of G minus 1. So you can save the extra color going from delta to delta minus 1, where of course you have to forbid omega being delta. But here we need to add, instead of delta being at least 3, at least 9. So why delta at least 9? This is a bit of a strange question, but the answer why they made it that way is because they had to. So namely, and I'll give you a picture, an even more general picture of this in a bit, but let G be C5, and that's the strong product with K3. So that's taking a C5 and blowing up every vertex to a triangle, and then putting all the edges in the cyclic way. And then if you look at that graph, if you stare at it, you'll realize that it has maximum degree 8, because you're adjacent to the 2 in your triangle and the 3 in each kind of neighboring triangle. You have omega being 6, because that's the largest you can find, 2 kind of neighboring triangles. And yet if you go through it, chi will have to be 8. So you won't be able to color it with 7 colors. And so what is that saying? Well, we wanted delta here with delta being 8, we'd want for Borodin Kostachka chi to be at most 7, and this fails that even when omega is 6 instead of 7. So somehow there are just lots of small kind of examples, a la the odd cycles a bit, that show why this won't work. So kind of maybe small finite number of examples, but showing that we can't hope this to be true for when delta is at most 8. However, maybe it's true for delta at least 9. So there's just something nice that happens in the spirit of Brooks' theorem if you exclude odd cycles. So here we just have to exclude kind of small delta cases, and then this could be true. And what is known about the Borodin-Kostachka conjecture is that it is in spirit true. So there is some delta from which it becomes true from then on. This was shown by Reed in 1999, who showed it was true for delta, a bit astronomical with 10 to the 14th, but maybe with some hard work could get down to maybe around 1,000, but it wouldn't, his methods wouldn't apply to get it down to 9, which would be very nice because it uses probabilistic methods. Part of the class we'll be talking about in the second half, and that would possibly work for 9, but maybe for like 1,000 or 1,000,000, but at least for 10 to the 14th. And so asymptotically or in spirit, for large enough delta, the Bordy and Kostachka conjecture was shown to be true. So that in some ways closes the book, even though this is open, on in spirit answering that, what about saving one more color? Okay, but now let's say we want to save a lot more colors. Then actually there's a very nice conjecture of Reed from 1998. It's surprising to me it took this long to make such a beautiful conjecture, and here it is that the chromatic number is at most delta plus 1 plus omega over 2, but rounded up because that'll be a fraction. And what is this number saying? Well, if you remember from our first lecture on coloring, we talked about bounds on coloring, because coloring's hard, it's nice to look through the lens of bounds, and we had an upper bound of delta plus 1 from Greedy, and a lower bound of omega, this clique number, because you need that many colors on a clique. And what this is saying is we have these two bounds, this lower bound and this upper bound, and actually the chromatic number is closer to the lower bound than the upper bound, modulo that rounding up. So this is a very nice conjecture, right? Where somehow the chromatic number is closer to its trivial lower bound than its trivial upper bound. Okay, so what's known about Reed's conjecture? So this is very it doesn't imply Brooks theorem, it doesn't imply the Bordy and Kostachka, because their omega would be delta minus 1 and you just find a delta, and in Brooks you put in delta and you round up and get delta plus 1, but it's in the spirit of that. It's saying, this is how we try to save more colors. But why the half? Why this rounding? Maybe you could think to do a lot more, and actually no, Reed's is tight. Essentially it's tight for almost all the cases. And here's how it goes. So we take a 5-cycle blow-up. So I had alluded before with the Bordy and Kostachka, this example where you take a 5-cycle blow-up, you blow up each vertex to a K3, a triangle. But actually more generally, this provides a somewhat tight example for Reed's. Here's how it goes. We blow up each vertex of a 5-cycle to a more general clique, a KT. And how does that work? Well, look at this graph. Its delta, that's the maximum degree, it's vertex transitive, so it'll have the same degree, is 3t minus 1, right? You're adjacent to t minus 1 other vertices in your own blown up clique, and the two other KTs, that leaves a delta of 3t minus 1. If you stare at it, you'll see that omega is 2t, made by two neighboring KTs, and that you couldn't possibly get larger, as then you get a non-edge. And what about the parameter of the right-hand side of Reed's conjecture? Well, if you take these together, delta plus 1 is 3t, omega is 2t, so you get 5t over 2 rounded up. And now, what about the chromatic number? Well, actually, here's a way to show that the chromatic number has to be at least that number, the 5t over 2. It's because the independence number is 2. There's no independent set of size 3. You can take at most 2 vertices for the largest independent set. And why is that important? Well, that's the independent sets make up the color classes, right? So every color class in the coloring is an independent set. So each color class, each color can only use 2 vertices at most. So how many colors do we need? We need at least 5t over 2, and since chromatic number is integer, then we have to round up. So that shows you that chi is at least 5t over 2, and actually if you understand fractional coloring, or if you just want to play with it, you can indeed color this example with that many colors by kind of cyclically doing the coloring. So it's not a counterexample to Reed's, but it's in spirit the tight example to Reed's. So we know Reed's is essentially tight for all these values, and there are other constructions as well coming from Ramsey theory that I won't really talk about. If you're concerned that this is only a tight example when omega's around 2/3 of delta, but there are actually ones you can get essentially for any value of omega in terms of delta. But now, subject to the examples I'll mention a bit, but for any fixed constant, you can do that. And now, where do we go from here? Well, what else was shown about Reed's conjecture? Well, you can't just make a conjecture. I mean, you can, but it's nice to make a conjecture with some evidence for it. So one evidence was this, I thought of examples, Reed could say, and here's this tight one, this construction, so that's maybe some evidence. I thought for a while, and I couldn't think of any more, but here's these nice tight ones. But actually he showed that it holds when first delta is sufficiently large, so somewhat maybe astronomical, maybe a 10 to the 14th or something, and importantly that omega is large. So we show that if omega is 1 minus, 7 over 10 million delta G, something like that, then you're actually, it just holds. This is very nice. So if omega is really, really large, 0.99999, times delta, then it holds, for at least delta being large. So actually this kind of then gives you more, again, that doesn't give you the boring Kostachka conjecture, but it gives you in spirit all that for any constant. So, if you wanted omega to be delta minus some constant, this would cover that at least for large enough delta. And even does it as then a proportion, multiplicative instead of additive. So that was very nice, and you could just combine this actually with Brooks Theorem, because this only holds when delta is large, but then if you understand Brooks Theorem, you could only say one color. If you combine those two, you can get the following nice result. There's some epsilon greater than 0, such that chi is at most the non-trivial convex combination of the two bounds delta plus 1 and omega. Namely, it's at most 1 minus epsilon delta plus 1 plus epsilon omega. So that's very nice. So this is again more evidence in spirit. Reed's is true, at least if you don't care about optimizing to that half. Okay, but what else could you ask? Well, we could ask, what about this epsilon? If you go through it, if you go through what Reed's value would give you, maybe it'd be something like 1 over 100 million. And that's not very pleasing, so maybe we could ask, can we improve it? And again, since all these techniques are going to be using probabilistic methods, all the known type proofs working on Reed's conjecture use probabilistic methods, let's just ask it for large enough delta. So none of this trick about using Brooks Theorem. And can we get closer to epsilon being a half than 1 over 100 million? And well, actually, there's been a lot of work on this over the decades then, and for large enough delta, we get this following epsilon suffices. So here's some of the history. King and Reed in 2012 had given a shorter proof of this result for Reed's about the epsilon, and there you end up with 1 over 320 e to the 6th, which is about 1 over 130,000, which is an improvement over the 1 over 100 million, maybe not a lot to write home about, but also the proof was much shorter. Instead of 40 pages, maybe 10 pages. And then I, along with Bonamy and Perret, showed that you can get away with epsilon being a 26th for large enough delta. So a big improvement there, and then with Delcourt, I improved this even further to a 13th. So for large enough delta, we could get epsilon being around a 13th to work. And then just recently this year, Hurley, Dionis, de Verklos, and Kang had improved this to somewhere around, say, 1 over 8.4 for epsilon. So steady progress. Again, all these papers are in succession, building on top of each other, coming up with some additional new ideas each time, but still using the prior work each time to inch closer toward a proof. And so I won't go into how that proof goes or anything, but just trying to show you the march of history here. And I don't know if there's some limit to all these barriers. I don't know if we'll ever really get to a half. Maybe there's a 1 over 2e or an eighth or some barrier from our methods, but in some ways, Reed's conjecture is really in spirit true, even with much better numbers now, that for this epsilon, that you really get a decent convex combination of these two bounds as an upper bound for chi. So that's what happens when omega is in the linear range. What about other omegas? Well, it's actually interesting to even just focus on the omega-2 case, which is triangle-free graphs. And even beyond triangle-free, large girth graphs. So if you haven't heard of girth, let me tell you what girth is. The girth of a graph G is the length of a shortest cycle in G. So if you have a triangle, then you'd be girth 3. You can't have girths 1 and 2 because we don't allow diagons. We're just talking simple graphs here. But if you exclude triangles, then you have girth 4. But if you also exclude 4 cycles, as well as triangles, then you get girth 5 and so on. And so this is girth. And here's a very nice theorem of Erdős from 1959, which had been open, and then he showed that for every girth, for every g and k at least one, there exist graphs of girth at least g and chromatic number at least k. So people wondered, can triangle-free graphs have arbitrarily large chromatic number? And Tat had shown that that's true, and there's things like the Michalski construction that do that. But Erdős was the first to show this for all girths. So if you want girth 1,000,000 and chromatic number 1,000,000,000, we can get that for you. And actually we'll be doing this proof later in this term, and it's very nice because this was the paper where Erdős introduced the probabilistic method. And he uses probabilistic method, in particular alterations, to show how to probabilistically construct these graphs. Now these aren't actual constructions. It was Lovász in the 70s who came along to give the actual construction, but Erdős was the first to prove that these exist. So that is telling you, okay, we can get high girth and high chromatic number, but how does that relate to our thing about degree? So what if you fix the maximum degree? Maybe you can do much better than Reeds. Well, actually, Fries and Woodcock in 1992 had shown that if you take d-regular graphs, in particular random d-regular graphs, so I won't tell you what those are, but there is some model which tells you how to randomly sample d-regular graphs, and you can study that with probabilistic methods. And they were able to show that random d-regular graphs have chromatic number at least on the order of 1 minus O of 1 d over 2 log d, that's the natural logarithm, with high probability. Now they also meet that bound with high probability, and they actually figured out kind of the error term as well with some precision. But essentially, random d-regular graphs, you can't do much better than d over 2 log d is the answer there. And why is that important? Well, it turns out that random d-regular graphs have, at least with some constant probability, a chance to be high girth. So for any girth, there's always at least some, maybe it's just very small, 1% or something, but here we know that always, like almost always, you have this chromatic number, and you put those two facts together, and you find that for every girth, g and d for degree, there exists a d-regular graph g of girth at least g, with chi being at least that d over 2 log d. So now we have a somewhat natural lower bound coming from these random d-regular graphs for large girth. So you can't hope, even if you're big, all the possible cliques and all the small cycles to do better than this. So what's known on the positive side, instead of lower bounds, upper bounds? Well, this is a very nice story for girth 5, and then I'll talk about triangle-free. So there's this very nice theorem of Kim from 1995. And it says that for every epsilon, at least 0, there's some delta large enough. So if G is a graph of girth 5, and its maximum degree is at least that delta, then you can get chi being at most 1 plus epsilon delta over log delta. So in spirit, you can get a delta over log delta there. Again, natural logarithm. Which doesn't quite match, unfortunately, that lower bound, and it's still an open problem of intense interest related to very hard questions in Ramsey theory to improve this. And if you ask me which one's true, the divide by 2 or not, I couldn't tell you. But that you have this very nice theorem of Kim that says that the right order up to the constant. And if you're not familiar with this, instead of this 1 plus epsilon, for every epsilon there exists delta notation, you might see it instead written this way, which is if G is a graph of girth 5, then chi is at most 1 plus little o1 delta over log delta, which are functionally equivalent. So that's Kim's theorem. What else was known? So what if you want to go to triangle-free, so allow force cycles? Well, Johansson, also in the 90s, had shown that there exists some c greater than 0, some constant, and his was maybe 9, though Malloy and Reed give a proof with 100 or something, that if G is a triangle-free graph, then chi is at most c times delta over log delta. So you can't get that, the very nice 1 there, but there's some constant which works. And his results were unpublished. You can find versions of them in the nice graph coloring book by Malloy and Reed, but they were hard to get access to. But he had done this, so you essentially extending Kim's to triangle-free case, Kim's theorem, but at the cost of the constant. But again, on the correct order. And well, actually, I just want to mention again, if you haven't seen this, instead of the there exists C version, you might instead see this, if you're not used to big O notation, as chi of G is at most big O of delta over log delta, and that just means there's some constant you could put in for that big O. So that was Johansson's theorem. Another breakthrough, and both of these use probabilistic methods, which we won't cover these proofs, but again, we'll be covering probabilistic methods in the second half of the class. And then just actually recently, you might think that's the whole story, Malloy in 2017 had improved this to match the bound from Kim, so that if G is a triangle-free graph, then chi is at most 1 plus little o1 delta over log delta. So basically, we now kind of, up to this very big division between the 1.5, know what happens for triangle-free graphs, and thus for graphs of all girths. So very satisfying, very nice results. And now, well, there's a lot of other ranges. We cover kind of the omega 2 case, we cover omega linear with reeds, but you can keep going. What if you want to exclude K4s and K5s? Well, Johansson had done this. For every fixed R, again, unpublished work, but he showed that if G is a graph with omega at most R, then you can actually get kind of delta over log delta, but you have to pay a price here. He needed an additional log delta factor, which would not, it's not conjectured to be tight. It's conjectured that you don't need this log delta term, but no one's improved on that. However, Malloy did manage to improve on this by, one, getting a somewhat better constant, so he has a 200, and he actually puts the omega into the thing, so 200 omega times that. Why is that good? Well, it's saying omega doesn't have to be fixed. You don't have to fix it to be 4 or 5. Rather, this would actually, if you think about it, give you a fairly good bound for any omega at most log delta over log delta. At least something kind of a bit better than greedy, at least up to the constants. So kind of when omega is in the sublogarithmic delta regime, then this Malloy's results give you pretty good bounds. So maybe not the best possible, but in beating things maybe from Reed's conjecture. So this is pretty good. You might ask though, what if omega of G is larger? So we've covered the triangle-free case, these cover the small clique number, Reed's handles large, but there's actually kind of something in between if you think about it. So here's a natural question, what if we want to do better than Reed's? So for every k at least 2, so fix some constant, 3, 10, etc., what value of omega guarantees chi to be at most delta over that k? So say we want to beat Reed's, we want to get to delta over 3 or delta over 10. What do we need to be true about omega for that to happen? So that's a very nice question, and we actually kind of resolved this. So this medium clique number case, so with the theorem with Bonamy, Kelly, and Nelson, we showed that chi is at most O of delta times the square root of log omega over log delta. So why is that nice? So the idea is we've traded a linear omega for kind of a log omega. And that's very nice, but at the cost of a square root. So it's conjectured you don't need the square root there, and that would actually be tight. But if you process that, if you work through it, you get the following nice corollary. It answers our question, at least in some spirit. For every k at least 2, if omega is at most delta to the 1 over, and it turns out the number we use would be 192k squared, so 192 squared is rather large, but basically if delta is on the order of a root, but with a 1 over k squared there, then chi would be at most delta over k. So as long as omega is kind of a small enough root of delta, then so it could be larger than the log regime, but some root regime, then you can get beat Reed's with any constant k. So this corollary and really the theorem above essentially cover those cases from logarithmic omega up into root, where omega is more the roots of delta. And actually, I'll just mention that Ramsey theory constructions show that we cannot extend this beyond something linear in k. So it's something like delta to the 2 over k minus 1. So it's open whether we can make that k squared into more like a k, extend it to larger values of omega, and that would be nice. And that's related to essentially getting rid of that square root in the theorem above. And we'll be talking about Ramsey theory later in the term, and not doing all constructions or things, but some basic, and how to use the probabilistic method to come up with constructions of Ramsey theory to create certain graphs with certain clique number, independence number, and thus chromatic number, etc. So this is a window into that. But today we've reviewed various aspects of this omega delta chi paradigm, and very nice results from the 90s through now on small clique number and medium clique number and linear clique number and Reed's conjecture and boarding Kostowska conjecture and all of these nice kind of conjectures, and we saw results from error notion on random regular graphs. So there's a lot of work there, and this is just, again, the tip of the iceberg. So here we haven't gotten into list coloring, so you could ask all these questions, not only as for Brooks for list coloring, which is in the homework, but also for all of these problems. And a lot of them hold in that context. Or you could, ask for other variants of coloring, or you could ask what if we don't just use omega in there. So there's a lot of other questions, tip of the iceberg with this stuff, but it's all in the spirit, all started from Brooks Theorem, from that classical theorem that says, when can we save one color? And all of these get to ask, when can we save more? Well, when can the chromatic number be even smaller by a lot? What conditions do we need? So it started a whole vein of research and led to all of these results. So that's the lectures for the week. We'll tune in next week for when we talk about edge coloring, when we move into a different segment of coloring and talk about various nice theorems there in regards to edge coloring. But I hope you enjoyed this window into Brooks Theorem and beyond.